Welcome back, everybody. We're continuing with Chapter 6 on forces, and this is going to be example 6.4. And it's yet another example of where we are going to take a force that is applied at some sort of an angle and break that into an x component and a y component. And what I'm going to do here is go ahead and just sketch them in. So we're going to have this force. That's going to be our force. I'll erase this little thing down here. It's going to be our force in the y direction. And we're going to have our force in the x direction right there. It is our only force, and so therefore it is the net force acting on this sled system right here. So let's take a look at this and see if we can make some sense of it. So we've got a sled with mass, right? It's got a mass of 4.6. I'll put m sub s, the mass of the sled, 4.6 kilograms. Okay. The force acting on it has a magnitude, so it's a full magnitude of 6.20 newtons. So the force right here is 6.2 newtons, and so what we're going to do is we're going to break that into an x and a y component. And it has an angle from the horizontal of 35 degrees. All right, that'll help us because we'll now be able to figure out what the x and the y components are. What is it asking us here? All right, you might think, okay, we've got a force and we've got a mass. Must be asking us for acceleration, but it is not. It is asking us for how fast is it going after a certain amount of time. What that's really saying is, what is the final velocity of this sled right here? All right. Now, you guys remember from kinematics that if you see something like this, starting from rest, that means, okay, well, the initial velocity is 0 meters per second. And as it changes its velocity over a period of time, it has a final velocity. Okay, and so what we're going to have to do is kind of bring in our knowledge of kinematics with our knowledge of Newton's second law. Now, before we do, one thing that should be pointed out is the direction of motion. Even though the sled is kind of being pulled in the x direction and up by the man pulling it with a rope, it's really only moving in the x direction. So the only component of this force that we really care about is the force in the x direction. What the y force is doing is actually serving to make the sled slightly lighter, right? It's making it less heavy, you might say, or give it less of a weight force, but we don't care about that. It's not coming up off the ice. Really, only this force right here, that force in the x direction, is the one that is moving it forward. Force in the y is not at all. All right, so let's go ahead and write that out. So the net force on the sled is really the force in the x direction. All right, that's what we just said right here. And so we can figure out what that is. That's going to be the full magnitude, so it's going to be F times the cosine of 35 degrees. All right, and in fact, I'll just keep it generic for now. Cosine of theta. All right, that'll give us our force in the x direction. And Newton's second law tells us that the net force, or force in the x direction in this case, should be equal to the mass of the sled. We had that so far, times the acceleration of the sled. Well, we don't have the acceleration. We don't know what that is, but we do have some components that can be described in terms of acceleration. For instance, we have the initial velocity. We don't have the final velocity, but that's part of an equation that deals with acceleration, and we have time as well. What I'm saying here is this. Don't we have an equation that looks like that? V final equals V initial plus acceleration times time. All right, if we are solving for a final velocity right here, why can't we take all the rest of this and put it in terms of acceleration and then substitute it in for that acceleration right there? Let's go ahead and do that. I'm going to rearrange this and solve for acceleration. So I'm going to do V final minus V initial divided by time equals acceleration. What that means is that we can take this, and since these are equal expressions right here, I can just take this and plug that right in for acceleration, and then the only unknown is my v final. All right, does that make sense? So let's go ahead and do that on the next page. All right, I need to kind of write down my my working equation again. So the net force equals mass. Oh, let's just stop. Okay, so I've gone ahead and taken the liberty of just taking all of our values, all of our knowns, actually, and some of our unknowns, like right here, and writing them down on this on the slide right here, so we can kind of attack the problem. Now, remember that the force that is applied is 6.2 newtons. All right, but it's applied at an angle. All right, so this force is applied like this, and that's 6.2 newtons, and it's being applied at 35 degrees north of east, or above the horizontal right there. What we care about is not so much the force itself, but we care about the x component of the force, because that is the direction in which the sled is actually moving. So we really want to find the net force in the x direction. The y component of the force really isn't doing anything at all. It's really just the x component of the force. So let's go ahead and solve for that. We can say for the x direction, all right, we can say the net force in the x direction equals, well, the force in the x direction, okay? Which is what? Well, that's the full magnitude times the cosine of the angle. So that's 6.2 newtons times the cosine. What's the angle? 35 degrees. All right, this will give us the magnitude, we should say, it'll give us the x component of that force. My calculator tells me that that is 5.1 newtons. Okay, in fact, I should write that in green, because I usually like to write my x values in green and my y in blue. So 5.1 newtons. I'm going to dotted line box that. It's not the final answer, but it's an important component to our final answer. So that's the net force in the x direction. We know the mass, of course, and so let's go ahead and write that out. So the net force in the x direction equals mass of the sled times the acceleration in the x direction. Well, we don't know the acceleration in the x direction, but we do know, kind of like we said before, that, I'll write this in red, v final equals v initial plus acceleration times time. So why can't we just take that and rearrange that and solve for acceleration? V final minus v initial divided by time equals acceleration. And by the way, all this is in the x direction. We're solving for our final velocity right here, so we can really take acceleration out of the equation. Well, we're not really taking it out, but we're just substituting it in, because if that acceleration is really that, we can take this whole equation right there and stick it right in there and solve for our only unknown, which is v final. So let's rewrite this out again. So the net force in the x direction equals mass times acceleration, yes, but we're going to substitute in our kinematics equation, times v final minus v initial over time. That whole expression is substituting in for acceleration. So let's go ahead and just solve for v final. And you'll notice I'm not even plugging in any values yet. We're going by our guess acronym. And so givens, unknowns, equations. So we're processing the equation. We're solving for the equation that we're going to substitute in at the very end. All right, so that's going to be net force in the x direction divided by mass equals v final minus v initial over time. Oh, you know what? And I can just bring my time up as well. So I'm going to put time up here. And then, because that comes up, mass comes down. And I'm just going to add my V initial on the other side. So V final equals, I'll make this a little bit neater here, net force in the x direction times time, okay, divided by mass plus V initial. Well, of course, that's going to not really matter anyway because it's 0. But now we have all of our values in the right location. All we need to do is solve. So V final, the final velocity of this sled, is our net force in the x direction. What is that? That's 5.1 newtons times our time. That should be 1.15 seconds. All right, divided by the mass of the sled. That's 4.6 kilograms. This just becomes 0, so we don't need to add it, and so all we need to do is just crunch our numbers and plug and chug. What do we get? I get 1.3, rounding up a little bit. 1.3 what? Well, it's velocity, right? So it has to be meters per second. That is the velocity of this sled after it's been pulled with this amount of force at this angle, starting from rest and for this amount of time. So we've brought kinematics into this because Newton's second law tells us that the net force is mass times acceleration. So wherever you have acceleration, you can bring kinematics in, initial velocity, final velocity, and time, and just substitute in wherever you have acceleration. So we did that. We solved for acceleration, plugged it in to Newton's second law, and we're able to solve for one of these unknowns right here, V final being 1.3 meters per second. So that's example 6-4, and I'll see you on the next one. Thanks for watching.